Awesome. So, good morning, everyone. Happy Wednesday. We're halfway through the week. Hope everyone is doing well. My name is Sharan. I'm a machine learning engineer at Airbnb. So today I wanted to take a little bit of time to sort of give you an overview of some of the crucial, or give you an overview of how machine learning works at Airbnb, where some of my work fits in, and generally talk about market dynamics in the travel and accommodation space, and specifically go into some algorithms and some interesting technical challenges that we face, so that I can share it with a broader audience and sort of and also propagate some of the learnings that we've had. Today's talk will be focused largely on optimal pricing. Pricing has been a core part of a lot of industries, especially two-sided marketplaces. And understanding these market dynamics have been extremely crucial in optimizing for revenue and profit in these kind of marketplaces. In when these kind of marketplaces are prevalent online, a lot of algorithms and machine learning techniques go into determining what an optimal pricing strategy is, and this optimal pricing strategy is in turn affected by market dynamics. So today I'll be focusing on what these market dynamics are and how we're going to talk about and how we address them at Airbnb. So the talk today will be split into three parts. Initially, I'm going to give like an overview of Airbnb and what two-sided marketplaces look like. Where does pricing fit into this entire scheme? And then I will go into pricing itself as a problem and try to motivate the problem statement, give everyone an overview of what we're talking about. And finally, I will go into some of the deeper technical challenges into what market dynamics affect optimal pricing policy, and talk about and sort of go into the algorithms and a little bit more into the weeds of the technicals. Awesome. So we'll start with Airbnb. I hope a lot of people have used Airbnb. If not, definitely try it. But at a high level, from a more theoretical standpoint, Airbnb is a two-sided marketplace in the travel and accommodation space. The company is trying to, as a platform, what we try to do is we try to match guests who are looking to make a reservation with listings or hosts who are looking to rent out their space for a few nights. Airbnb sort of fits in the middle and tries to find the best guest and tries to find for every guest the best listing among all the inventory that's available. If there are 1,000 listings and there are 5 guests who are searching every day, the goal here is to match every guest to the optimal listing that given a set of search parameters, etc. So as you can imagine, and all this happens on our platform online. So as you can imagine, when a guest comes onto Airbnb.com, they go through a few different experiences. So there are several factors that influence this matching process. For example, how relevant, how are our results relevant for the user in terms of search, both ranking as well as experience? Are we showing them prices that they really like? Do they trust our platform? And are they getting a sense of trust from us? And finally, they go through all the payment processes and we make sure all that is good. The larger goal here is to try and find for that guest an optimal listing, and optimality comes in several flavors. Can we rank optimally? Can we price optimally, etc.? So today I will be focusing on the pricing aspect. And the reason why this is interesting is because as with most machine learning problems, there's no one clear answer. Every guest on the platform is always looking to find the best listing at the cheapest price. Every host on the platform is always trying to find the best guest at the highest possible price possible. Because the host always wants to optimize for revenue and the guest always wants to get a really good deal. So there's always some amount of, and that's where optimization comes in, because we really want to find that optimal price point, which not only maximizes revenue for the host, but also helps take into account guest preferences and get a great deal for the guest. So that was a very quick overview of Airbnb. And I mean, what I would like to do now is sort of go into what I mean by pricing and motivate the problem statement a little bit more. So pricing at Airbnb essentially is a very host-facing feature or product. So what you see on the left is a typical host calendar, which is um, which is surfacing prices that the host has set for every night. So you can see in a few places here that the host has set $44 on a Sunday and 51 on a Wednesday, etc. And these prices are sometimes set by the host, but are often our hosts don't have full understanding of the market ecosystem. They only know about what's going on with their listing, which is a lot of information, but they don't have a very great sense of the broader market dynamics outside of their listing. In order to help them price every night on their calendar, we at the pricing team provide them with price recommendations that help optimize something. This something could be profit, revenue, occupancy, whatever. But the point is that we try to help them optimize for their requirement, not only accounting for how good their listing is, but also playing to the market dynamics outside of the system. So the larger goal of the pricing team is essentially, or the pricing product, is to provide a recommendation for every night on the calendar and do this for every listing on the platform and do this every day. So as you can imagine, the largest, as with any kind of theoretical pricing problem, you always have a supply curve that sort of increases with price. The more, if I go tell people, residents in Tahoe, that they can fetch, that every night in Tahoe can fetch $1,000, then the number of listings in Tahoe that are going to be hosted on Airbnb is going to skyrocket. But the number of guests who are looking to book that same listing isn't. So there's always a supply demand trade-off, and we would like to find a price that optimizes on this frontier, which is the green zone there, and that's essentially what the optimal price range would be. So if we quickly take a minute to think about what kind of market dynamics really affect this kind of pricing problem, we can split it up into three different domains. So we have spatial factors that influence it. So things like where your listing is really affects how much you price your listing at. And spatial factors come in various different flavors. It could come in macro or micro flavors. So macro would be like administrative boundaries, countries, zip codes, states, cities, etc., travel corridors, and micro being more like smaller neighborhoods, hyper local zones, etc. Besides spatial, we also have temporal attributes, so things like seasonality, events, lead time, etc. And we also have intrinsic properties of the listing, so things like how good your listing is, or how big it is, what kind of reviews you've got, etc. Also influence what kind of price you can set for this listing. So today I will largely be talking about, and as you can imagine, all these three factors sort of interplay with each other. You can never have one without the other, and neither can live by themselves. So today we'll be focusing on lead time, which is a very important temporal aspect of things. The reason why so that's a high level overview of the pricing problem. So the takeaway from the previous section was that the goal of the problem, or the goal of the pricing problem, is essentially to find that one optimal price that you want to set for January 1st of 2021, which maximizes your revenue, but also you want as high a price as possible so that you definitely get booked with the best revenue that you can possibly fetch. But you don't want it too high, because if you have it too high, then guests are not going to come in and book your listing. So how can we model this problem in such a manner that we can really nail down on this optimal price? And while we're doing so, we bear in mind that lead time dynamics play a very important role. What are lead time dynamics? I'm going to go into that in the next section. So a very quick primer on lead time. Let's say I was sitting today on December 1st, and I was looking to book a trip with a check-in date of New Year's Eve. In that case, the lead time here would be 30 days. The date on which I want to take the trip minus today would be the lead time to the trip. As guests come into the platform, They tend, as guests come into the platform, they tend to book at various different lead times. And the lead time of this lead time essentially refers to the time between the date of booking and the trip check-in. Taking a trip with a check-in of New Year's Eve, being booked 30 days in advance would mean a 30-day lead time. If you're going to book on the same day, so if I was sitting today looking for today's check-in, then the lead time would be 0. Guests will continue to make bookings for New Year's Eve as time progresses going towards New Year's Eve, and can make bookings right up to the end. This booking process reflects the inflow of demand and can be treated as a stochastic arrival process, as in a standard queuing theory formulation. And the corresponding distribution of bookings over lead time would be termed as the lead time distribution of bookings. So the logical question that anyone would think of is, why model lead time, right? Like what's there in lead time? How is it connected to pricing? So the plot on the left here shows how demand would look like at different times of the year. So as you can imagine, there are some weekly patterns there. And then on New Year's Eve, we see a spike because everyone would like to take a trip for New Year's Eve. And then it sort of goes back to normal. And there's also some seasonality over the summer, which I haven't really shown here. Airbnb, we came out with this product called Smart Pricing, which allows hosts to give control of their prices to Airbnb, and we modulate these prices in accordance with demand, supply, seasonality, etc. The main reason that we want to model lead time is because even if we choose a check-in date, even if we choose, say, December 25th as a check-in date, the kind of demand that comes into December 25th varies as we progress towards it. In other words, as lead time gets shorter or longer, the demand for the check-in date changes significantly. This demand also changes with the area that you live in, which are the spatial characteristics that we mentioned before. It also varies with the kind of listing that you have, and also takes into account temporal factors like whether there are events or not. A nice intuitive example here, an interesting one, is that if we think about a high demand night, for example, New Year's Eve or Easter, these high demand nights generally tend to get booked out far, far in advance, 90 days in advance, 100 days in advance, etc. And if we really take a supply constrained market, in these kind of markets, you can expect all listings to be booked out far ahead in time, which means our pricing policy needs to reflect the fact that bookings are going to come in really early, and we'll need to change our prices somehow in accordance to this to this kind of process, so that we can fetch our hosts optimal revenue and give our guests the best deal as early as possible. On the other hand, if we're going to have a really low demand night, or we're looking at an extremely demand constrained market, in such a scenario, bookings would generally come far, far later, close to the check-in time, maybe a few days in advance. So we may want to keep our prices as low as possible as high as possible initially, and then sort of tip them down so that we can accommodate the demand, or vice versa, whichever is the optimal pricing policy. This is the reason we want to model lead time dynamics. We want to know when demand is going to come in for a certain night so that we can adjust our prices accordingly, very simply put. Here's a more concrete empirical example of what a lead time process would look like. This, for example, is the booking distribution for San Francisco, with some of the numbers blurred out. Every bar here represents what fraction of bookings for a certain night, let's say December 1st, comes in at the lead time specified by the x-axis. So for example, in the region that I've circled, it means the mass density of bookings at a 7-day lead time would be, say, 5% or 6% or whatever. To formalize this a little bit better, if x of t be the distribution that we're looking at, we want to find the probability that a certain listing is going to get booked at a lead time of, say, 10 days, given that it is going to be booked. In other words, if I know that a listing is going to get booked, and I know that the probability of that listing getting booked is, say, 30%, then I want to distribute that 30% over the lead time axis in order to finally arrive at the lead time distribution, or in what we, analogously, what we call the arrival process. So the goal here is to model that mass density xt of t. Not only do we want to model it, we want this kind of distribution for every listing, for every night on the calendar, and for every lead time going into that night. So if you remember the calendar view that I showed you, hosts want to price every square on that calendar. And these prices need to change every day because hey, demand changes every day, supply changes every day, competition comes in, etc. So we want to get this distribution for every listing on the platform, for every calendar night, and every lead time. So, well, hey, I'm a machine learning engineer. So what do you do directly? Can you like directly go to machine learning, like use our normal conventional brute force approaches to try and estimate the density directly? I mean, we could capture all the training data that we think is indicative of the lead time distribution, demand, supply, competition, listing attributes, whatever we can think of. We can have our labels, and we can go ahead and predict these things directly. But it comes with a bunch of challenges. This distribution that you see on the left is what we're trying to predict. And using a straight up machine learning approach sort of breaks down in a couple of different axes. So one, machine learning in general doesn't account, like if we just directly predict our outcome variables, it doesn't really account for the probabilistic outcome that we're expecting. What we want is to say that December 31st has a distribution of lead time in this kind of manner. We don't want to say that December 31st has an average lead time of 30 days, or December 1st has an average lead time of 20 days. We want to say, we want a density curve over the lead time axis for every night in the future. And machine learning models in general would not account for this unless explicitly stated for. A second important factor is the sparsity of bookings. Every listing for every night in the future can get booked once and only once. This is an extremely sparse data point if you really want to use this one data point to arrive at a distribution for that particular night, especially for a night that's not been booked. So bookings are fairly sparse, and we want to account for sparsity and massage it in such a way that we can actually solve this formulation, even though there's a dearth of bookings. High dimensionality. So unlike more commoditized travel platforms, every listing on Airbnb is extremely distinct and unique from each other. There are no two listings that are the same, and while this is fantastic for our guests, giving an extremely large slew of options, it's a modeling nightmare because with every listing being different from each other, you have no consistency with features, and it makes every listing unit an extremely high dimensional data point to model. And finally, we have the scale of the problem. We have order of 1 million listings on the platform, and each of these listings say we want to model 1,000 nights into the future, prices for 1,000 nights into the future, which is like 3 years. And for every night, let's say we want to model 100 days in advance. Then we're really easily looking at least 1 trillion predictions every single day. And 1 trillion predictions for a machine learning problem, while it's doable with extremely good infrastructure that we have today, it sort of becomes intractable when done at scale. So what do we do? Is there some other consideration that we can think of? Just looking at that distribution above, like the first thing that stood out to us was that, hey, there are two things going on here. One, demand is decaying with lead time. By and large, there is some kind of connect there. It's not always decaying, but it's sort of gradually decaying with time. Maybe there's a unimodal or a bimodal peak somewhere. And the other clear thing that stands out are these cyclic patterns that come in. Okay, great. If I were the machine and I wanted to do it, I would have this kind of knowledge in my mind and then go about modeling the process. This was something that immediately stood out to us. So this sort of, so taking a step back and zooming out, we can arrive at two different schools of thought. We can either go towards the most conventional machine learning approach or a more structural approach where we're saying, this is how the lead time distribution looks like, and we want to model it explicitly in terms of these parameters. If we go for the conventional machine learning approach, we have excellent predictive power, but it doesn't scale very well. And most importantly, it doesn't model the underlying data generation mechanism. It doesn't model how bookings are coming into the platform. On the other hand, if I impose structure to the problem, we get much higher predictive power. We can build our own custom models, and at the same time, it does model it does model the data generation mechanism. So there are trade-offs. There are pros and cons to both of these schools of thought. But what we did is to try and marry both of these schools of thought for a final solution. So what I'm going to do next is sort of go into explaining how we predict this kind of arrival process in a very, and I'm going to do it fairly swiftly, given that I've motivated the problem. And it's done in 3 different steps. These 3 steps amalgamate the 2 schools of thought that I outlined before, structural modeling as well as conventional machine or deep learning, in order to finally arrive at a solution that accounts for these 4 problems that I've stated, accounting for probabilistic outcomes, sparsity, dimensionality, and scale. Can we tackle these 4 problems by combining these 2 different schools of thought is what I'm going to go into in the future, is what I'm going to go into in the next few slides. So quickly jumping into it. Step 1, we have a lot of listings on the platform. Every listing is different from one another, as I've mentioned. So the first thing that we wanted to do was address this problem of extremely high dimensionality and scale. And we did this by a technique we called as supply pooling. Since there's so much heterogeneity in these listings by virtue of price and quality and geography, all this sort of affects demand. And what we can probably do is take all our listings, segregate them into clusters such that each demand cluster is characteristic of a certain demand profile. Maybe these are the kind. So for example, if I took all the listings in San Francisco and I clustered them, maybe I would get a bunch of listings that are extremely residential, and some of them are which are extremely suitable for university housing, or some that are very close to the beach. If we're able to supply this kind of demand, pool this kind of supply, then what we can get at the end is clusters of listings that share very similar guest preferences. Meaning, if I was a guest looking to make a booking on Airbnb, then I would very likely look within this cluster. If there are 100 listings in the cluster, I'd make a choice within these 100 listings. In other words, these 100 listings are competing for the same guest vis-a-vis myself. Very likely, these 100 listings are also going to share the same geospatial attributes because people want to go to one place, they have a place in mind. They also share similar listing characteristics. If I'm going with a party of 5, that's not going to change. And we also, for modeling purposes, wanted supply balancing, which means if I want to build out machine learning models on clusters of listings, we want these clusters to sort of be IID and also be of sort of similar sizes so that we can use this not only for modeling problems, but also for analytical purposes. Finally, we wanted zoom hierarchical attributes, meaning we want to look at clusters at a hyper-local neighborhood level, as well as a much more zoomed out market level. Because market dynamics, as you can imagine, changes at a market level. Maybe it's high season for San Francisco, low season for San Francisco, but maybe if there's a NIPS conference that's going on at Stanford, that particular hyper-local geography is facing a demand spike. So we'd really like to account for these. With these in mind, we sort of use how do we go about clustering these listings. I'm not going to go into too much of the technical details of it, but I'd like to share some general intuition in the interest of time. When guests come into the platform, they view our listings in sequence before they go about and make a booking. They view listing 1, 2, 3, and then some other guest in comes views listing 4, 5, 6, 7, and then they go out to make a booking. Maybe guest 1 books listing 1 and guest 2 books listing 2. There is some sense of correlation that we can capture from this. It's these 2 listing view sessions for guest 1 and guest 2 sort of tell me that listings 1, 2, and 3 attract the same kind of guest. Listing 4, 5, 6, 7 attract the same kind of guest. And what we'd like to do is combine listings in such a manner so that the listings in one cluster cater to the same kind of guest preference. Maybe listing 1, 2, 3 were beach facing and 4, 5, 6, 7 were university housing listings. We take a standard NLP problem to this kind of approach. So you can think of words listings being words, guest view sessions being sentences. And what we want to find is embeddings of words vis-a-vis listings so that we can take a high dimensional listing and encode that into, say, an 8-dimensional vector that I've indicated below. Once we have an 8-dimensional vector for every listing, life becomes a little simpler. We move down from millions of listings to maybe in the high thousands. And what we can do thereafter is partition it. We have we have an internally developed recursive partitioning tree, which takes listings in the whole world and sort of breaks it down hierarchically to form clusters. And these clusters can be viewed at various different zoom levels. So for example, in the left, we've taken one market, split it into a child of left and right, and then done this recursively at various stages. So now we've tackled 2 different things here. We've tackled 3 different things here. We've tackled scale, in some manner by reducing listings to clusters. We've tackled dimensionality by encoding listings as embeddings, and we've tackled hierarchy by forming this recursive partitioning tree. Okay, great. Now we have clusters. What do we do with them? Here are some examples of interesting clusters. These are more for visualization purposes. They are real clusters now. So for example, for those who are fond of skiing, on the leftmost, you can see a set of listings that are very close to South Lake Tahoe and perfect for the summer getaway, some that are very close to the Squaw region and some that are slightly outside of Tahoe. So these are like 3 different listing clusters that we see in Tahoe. I've also given some illustrative examples of what these clusters would look like on the beach in Copacabana or the Bay Area itself. Hierarchy would look something like this. So for example, once we do that partitioning for say Florida, what we'll get is all listings in Florida, just South Beach, and then smaller neighborhoods within South Beach. Great. So that's part 1. We've taken our listings and made them into clusters. Things become a lot more simpler now. That's the machine learning side of things. We also noted, if you remember, that we noted that arrivals follows a certain distribution, and this distribution has a cyclic pattern to it. So what we can do is convey this information, this intuition that we have, to the model and say, hey, when I'm predicting this distribution, I would like to parameterize it in a certain manner. When we looked at this distribution empirically, what we noted was guest bookers who came into the platform had inter-arrival times that were exponentially distributed in some lambda. Okay, I'm sure a lot of you know where I'm going with this. If inter-arrival times are exponentially distributed, the number of bookings that you'd get in a unit interval of time would be Poisson in lambda, and the time to the event, which is the time to the booking from the check-in date, would be gamma in some alpha and beta. Okay, so if we knew this, then what we can do is impose this kind of parametric functional form on top of our distribution. And what we get at the end is the FB of P parameterized by alpha and beta, which just say that this arrival process is in fact gamma in nature. The equations below correspond to the mass and the cumulative density. Great, we did this, but we also noted that there were cyclic patterns in it. Can we add this into our formulation somehow? We can. All we need to do is consider this arrival process as a waveform now, detrend it, apply our usual FFT or DFT transforms, find the peak frequencies, and once we do this, we can model the cyclic patterns to how many ever harmonics we find suitable, as FC of t being rho sine omega t plus 5. So now we have 5 different variables that we can predict: the alpha and beta of the gamma distribution, as well as the omega, phi, and the amplitude of the cyclic patterns. Great. We've now narrowed down, say, these 100 data points that we see on that distribution to 5 parameters that we've now imposed a functional form to. Life becomes a little simpler now. Once we do this, there's a final piece to the puzzle. We have clusters, we have parametric functional forms. We can go ahead and predict for each cluster and for every night on the calendar what these 5 parameters would look like. as our machine learning problem. This is far simpler than taking every listing, every lead time, every night on the calendar and predicting values for that. I'm going to pause there because it takes a little. It took me a little bit of time to digest that fact. We're reducing the dimensionality significantly. By doing so, we're at least improving on our scale by a factor of 1,000 minimum. What we get at the end is, for every cluster, what we can do is build out our training data with predictors that we think with features that we think are predictive of this arrival process. Great. Our labels here would be the empirically fitted lead time distribution, our empirically fitted alpha, beta, omega, rho, and phi. And what we can find is we can model this process now as a maximum likelihood problem, where we're trying to find the parameters, these 5 parameters that maximize the likelihood of the arrival process being as such. And once we do this, we get plots that we see on the left and the right. So the red distribution is the empirical version, and this is a toy example. So the left distribution is the empirical lead time distribution, and the red one, and the green represents the fitted distribution of the arrival process. So you can see that it has a fairly good fit both on the mass and especially on the cumulative scale. And it turns out that for pricing purposes, you'd rather use the cumulative than the mass density. This is largely how we go about pricing. So instead of taking the smallest unit of prediction, which is listing, night, lead time, we aggregate it and do it in bulk.
Yes, Sharan, sorry to interrupt you.
Yeah.
We are running out of time.
Okay,
And
I'm
also
going to finish.
We have a question.
Yeah, I'm going to finish in one slide, Lena.
Sure. Okay.
Okay, thank you. All this comes for a cause, right? So for example, besides pricing, we also have some excellent side advantages to this. For example, people who travel to LA want to know how far in advance they need to book. So we give them this kind of information. In addition, we know that, for example, on the right side, smart pricing also uses this kind of lead time distribution to tell guests that, hey, to tell hosts that, hey, 22% of guests are making bookings, are very likely to have made bookings by a certain lead time. So maybe you should decrease or increase your price. We get these kind of additional insights in addition to the actual price. And we love giving these kind of insights to our hosts and our guests in order to maximize conversion on the platform. Final thoughts. From a machine learning practitioner's perspective, imposing this kind of explicit relationship combining structural and machine learning models really helps formulate the problem a lot better. It isolates the effect of critical variables that we really care about, and most importantly, models the data generation mechanism that we're trying to impose on top of the data. It can also help a lot with dealing with imperfect training data, which I'm sure a lot of you have faced, and dealing with truncated data. Structural modeling can really help bolster the machine learning process. That's all I had for today. Thank you so much for tuning in. I will now